So today we're going to talk about something called a limiting reactant. So let's think about what those words in general mean. Okay, what is a reactant? It's going into our chemical equation as a starter, right? We got to put in a reactant to get out a product. So reactant is what we start with. What does it mean if something is limited?
It's restricted.
Yeah, restricted, right? We can't, I can't use the word limit in its definition. Okay, so limiting means it's going to, restrict or dictate how much of our product can be formed. Okay, so a limiting reactant is essentially one of our reactants will get used up before the other. Okay, one of our reactants will get used up before the other. And so we're going to be able to calculate which of those reactants will get used up before the other based on its molar mass, based on how much we started with, all that kind of stuff. Okay, so if we say we put in 1 gram of hydrogen and 1 gram of oxygen into our equation, those are two very different amounts of their substances, right? 1 gram of hydrogen is a whole mole, but 1 gram of oxygen is a small fraction of a mole. So when we talk about our amount of substances in grams, it can be a little deceiving. And so we're going to look at which of our reactants can limit the amount of products that can be formed and all that kind of stuff. So to introduce a limiting reactant, we usually use a recipe to help us do that. So when you're cooking, right, how many of you cook at home? Yeah, a few of you. Okay, good. When you're cooking, most of the time you follow a recipe, okay? And when I want to go make a recipe, I have to look, do I have all of the ingredients, right? If a recipe calls for 5 cups of flour and I only have 2.5 cups, how much of the recipe can I make? A half, right? So that limits my product. Does that make sense? So in our example right there, flour would be my limiting reactant, right? If I needed 2 cups of sugar and a stick of butter or whatever, and I have everything else except I only have 2.5 cups of flour and I need 5, right? That's my limiting reactant. Does that kind of make sense? It's going to run out before everything else, so it limits the amount of product that I can make. Okay? So if I'm going to make a cheeseburger, right? I need a hamburger bun, a tomato slice, lettuce, cheese, and burger. Okay? That's my recipe for a double cheeseburger. So if I want to make 5 double cheeseburgers, how many hamburger buns do I need? 5. Okay, how many hamburger patties do I need? 10. Okay, how many slices of cheese do I need? 10. And how many slices of tomato do I need? 5, right? So if I don't have all of those things, I can't make 5 of my product. Does that make sense? Okay, so if I start with these ingredients, how many cheeseburgers can I make? Okay, if I start with 1 bun, 2 patties, 2 slices of cheese, and tomato, right? We're excluding lettuce. Let's say we have excess. How many can I make, right? Excluding lettuce. Let's say I have extra lettuce.
0.
I can make 1, right? Assuming we have extra lettuce. I only have 1 bun, which is top and bottom. So 1 bun put together is top and bottom. Okay, so I can make 1. If I have 2 buns, 4 patties, 4 slices of cheese, and 2 tomato slices, how many can I make? 2. This doesn't change. How many can we make?
1.
I can't make 1. I can make 1 mole of cheeseburgers. Okay? So how many can I make?
1.
1. I can only make 1. Why can I only make 1? I only have 2 slices of cheese, so which is my limiting reactant in this case? Slices of cheese, right? Cheese would run out. So if I have an assembly line and I'm putting together, my cheese will run out after I make 1. So I can have all the excess buns and patties and tomato that I need, but those are excess. Okay, what's it mean to be excess? Extra, leftover, right? So I would run out of that, and that means I can only make 1 cheeseburger. Okay, understood? Okay. Okay, we just talked about this, blah, blah, blah. If one of our ingredients gets used up during our reaction, that's called our limiting reactant. And you'll see me label that a lot of times as just LR. So limiting reactant, if I abbreviate that, that just goes, it's going to be a capital LR. Okay, the limiting reactant limits the amount of product we can form. So the example we just used was double cheeseburgers, or we looked at an example with cake, right? I was going to run out of flour. That's my limiting reactant. So it limits the amount of product that we can form. We do the same thing with our chemical reaction. So now we're switching gears from food to experiments, right, or chemical reactions. We're going to have two starting amounts of our compounds. So every stoichiometry calculation we've done so far, we've been given one starting amount, right? We would start with 20 grams of one of our reactants. Now we're going to be given two starting amounts, and we have to determine which of those will get used up first, which means that would be our limiting reactant, right? It would limit the amount of product that we can make. So now our T-chart work goes from maybe one T-chart. Now we're going to have 2 or 3 or 4 per problem. Okay, so we're going to have to do a lot more calculations. Okay. We're going to look at the formation of ammonia here in our chemical reaction. Okay. The chemical reaction or the balanced chemical formula is essentially the recipe, right? I need 1 mole of nitrogen gas plus 3 moles of hydrogen gas in order to produce or to yield 2 moles of ammonia, right? That's my recipe. I have to have 1 mole of nitrogen gas, 3 moles of hydrogen gas, in order to yield 2 moles of ammonia. So it has to be in that ratio, right? So this part up above, you don't have to necessarily write that down, but I want you to look at this question that's in bold down at the bottom. How much ammonia could be made if I start with 2 moles of N2 and 3 moles of H2? Just think about it for just a second, right? Think about what's going to be our limiting reactant here. Okay, so how much could we produce? 2 moles of NH3, that's correct. So which of those is my limiting reactant? H2, okay? So let's think about how many of you totally get that? And how many of you are totally confused? Okay, that's okay. Totally confused. Okay, so what's happening here is we have to start with 1 mole of N2 and 3 moles of H2 in order to yield 2 moles of ammonia. Are we on the same page with that? Okay, so now I have my starting amounts. And I have 3 moles of H2, which is exactly what I need, right? But how much of N2 do I have?
2.
I have double what I need, right? I'm starting with 2 moles of N2. So I have exactly what I need of hydrogen, and I have double what I need of nitrogen gas. So which of those is going to be used first? Or is going to run out first? My hydrogen gas, right? Because I had exactly what I needed. My other one, I had twice as much as what I needed. So I can only produce 2 moles of ammonia. Does that kind of make sense? Yeah. We will not do these calculations in our head. We're still going to put them on paper. But I want you to understand the concept behind of where this is coming from, right? Why these calculations work the way they do. Okay? You have a question?
Isn't it 2 N on both sides?
What do you mean 2? There's 2 nitrogens on both sides.
Yeah.
But this is N2 gas. So that's nitrogen gas. It's a diatomic. On the other side, it's not nitrogen gas anymore, it's ammonia. So it's bonded with hydrogen. So in order to balance, we had to have 2 moles of that. Okay? Okay, question so far. Do we understand the concept, at least, of limiting reactant? One of our reactants is going to run out first. One of them is going to be considered in excess, right? Or it's going to be left over at the end. Okay. Blah, blah, blah. Okay. We just talked about that. All right, let's try this one. What's the limiting reactant when 82 grams of copper reacts with 25 grams of sulfur? So we can't just look at the starting amounts and say, oh, the smaller amount of grams is going to run out first. That's not always the case. It has to do with what their molar mass is and the mole ratio within our problem. So it's a little more intense than that. So what we're going to do to look at limiting reactant is we're going to have to basically do 2 T-charts, one with each of our starting amounts. Okay? Here we only have one product, so we're going to go to the product both times, right? We're going to find out how much of our product could be formed based on each of these starting amounts. Okay? If you would have 2 products, you would just pick one of them, and you'd go to it in both T-charts, but I'll explain that here in a second, okay? So let's see. I'm going to start with 82 grams of copper. And I want to find out how much of copper sulfide could be produced. Now, since our problem doesn't say anything about percent yield, it doesn't have any other questions that go with it, you can just stop in copper sulfide at moles if you wanted to. Okay, we want to find out which of these starting amounts will produce the least amount of product. That would tell us which of these is going to run out first. Okay, so we don't have to go all the way to grams if we don't want to. We could stop at moles. Does that kind of make sense, or did that not make sense at all? Okay, well, we're going to go with it because no one's saying anything. So we want to go from grams of copper to moles of copper. Then we'll go from moles of copper to moles of copper sulfide. Okay, and because it doesn't ask us specifically for grams, we can just stop at moles, right? Because you can compare your amount of product in moles and moles. Okay, so what's the mass of copper? 63.5. And the molar mass, no, we don't need the molar mass. The mole ratio between copper and copper sulfide is 1 to 2. Right? Do you see where those numbers came from? From our balanced reaction? So I'm done with grams of copper, I'm done with moles of copper, and I'm left with moles of copper sulfide. So get that calculator out. Okay, so what this is telling us, this T-chart is telling us, if we started with 82 grams of copper, we would produce 0.646 moles of copper sulfide. Okay, so right now we haven't answered our question. We've just given ourselves a possibility. So if we used up all 82 grams, we would produce 0.646 moles of copper sulfide. Okay, but we haven't answered our question yet because we don't know which of those is going to run out first. So now we do another T-chart from our other starting amount, so 25 grams of sulfur, and we have to go to the exact same thing, right? So we need to go to moles of copper sulfide. We can't compare moles of copper sulfide and grams of copper sulfide. They don't, compare the same way. So we'll go grams of sulfur to moles of sulfur. And then we do our mole ratio step. Okay, so did we get it to come out at about 0.78? So which of these is a smaller amount of moles, right? Which one is smaller, the first or the second one? The first. So this produces a smaller amount of our product, which means our limiting reactant is copper. Okay, that means if we used up all of the copper, we would produce 0.646 moles. If we used up all of the sulfur, we would produce 0.78 moles. But we're not going to get the opportunity to use up all that sulfur because the copper will run out first. Okay, does that part make sense of what the T-chart is telling you? So when you find your smaller amount of your product, you have to go back and say our limiting reactant is copper, right? Don't circle this and call it your limiting reactant because that's your amount of product that can be formed, right? Your limiting reactant is the starting amount or the reactant that you started that T-chart with. Okay, what questions do we have here? So we just found our limiting reactant. What's the maximum amount of copper sulfide that could be formed? So we know the answer to that question. How many moles is it? 0.646. Right? We're not going to get the opportunity to get all the way to 0.78 because the copper will run out first. It's limiting the amount of product that can be formed. So the maximum amount that we could form has to be based off of what the limiting reactant could do. Okay, any questions here? I know this seems really foreign and really like a lot of work, and it is, but it's just about getting that pattern down. It's about understanding what you're converting in your T-chart. Okay, if you're just putting in numbers and you don't have any clue about what you're doing, it's going to seem really confusing. Okay, so you need to take the time to really understand what those numbers are telling you. Okay? If this would have asked for grams specifically, how many grams of copper sulfide, you should have just taken your original T-chart all the way to grams of copper sulfide. Okay, but since it didn't ask us specifically for grams, that's why we stopped at moles. Does that part make sense? If it would ask you specifically for grams, you should just do it grams all the way at the beginning. Okay? Because if it asks for grams, now we have to convert it, and that's just one extra step, right? So you need to look ahead on these types of problems and see, okay, am I going to need to use percent yield, in which case I would need grams, or all those kind of things. Okay? So just make sure in these limiting reactant problems you look ahead a little bit. Okay? Do the reaction twice. We went to grams on these. We didn't really have to. Okay. I did way too much work on these PowerPoints. Okay. What's the limiting reactant when 6 grams of hydrochloric acid reacts with 5 grams of magnesium? Okay. Here's the thing about this balance reaction. Okay, I balanced it for you. We have 2 products. To find our limiting reactant, it makes no difference which product we go to. It makes no difference. But you got to go to the same product on both your T-charts. Okay, because we can't compare moles of hydrogen and moles of magnesium chloride, right? They don't mean the same thing. So you pick one product and you go to it both times. Okay, so which product would you probably pick here? Right, probably H2 just because it's smaller, right? And we're going to go to moles, so it doesn't really matter anyway, but if you were going to grams especially, and this one says look for grams of each product. So we're going to go ahead and go to grams of both of them, okay? So we're going to start with our starting amount of HCl, so 6 grams of HCl. And what is our final goal going to be here to solve for? Grams of H2, very good. Okay, so I'm starting with 6 grams here, and I'm starting with 5 grams of magnesium. Does the T-chart process itself at least make sense to everyone? Is everyone feeling pretty comfortable with that part of it? Okay, give me like a head nod if yes.
Why did you go to H2?
I just picked one of them. So it doesn't matter which product, one of the products. It doesn't matter which one you pick. In some problems, if you look ahead, right, it might ask for the percent yield of hydrogen gas, in which case you would just automatically know, okay, I need to go to hydrogen gas. Okay? I had a pretty small number of grams, 0.164 grams here of H2. Yeah? Okay, good. So our next one, we'll start with grams of Mg, and we want to go to what?
H2.
Still grams of H2. So we got to go all the way to the same product. Yeah, Isabel? That's kind of hard to see. I got about 0.411. Okay, so which of these reactants is our limiting reactant?
HCl.
HCl, good. We pick the T chart and we go back to the beginning. So our limiting reactant equals HCl. Very good. Okay, because it produces the least amount of our product. That means this would be the maximum amount of product that could be formed. Okay. In both of the problems we've done so far, coincidentally, the larger amount of the larger number of starting grams ends up being our limiting reactant. So you have to understand it's not necessarily whichever one you start with less amount of grams, that's not your limiting reactant necessarily. Okay, because for both our examples, it's been the other way around. Okay, let's try this one. Let me find your... Okay, if this many grams of ethylene are combusted, so you need to we'll write the product or the balanced reaction together. If it's combusted, what does that mean our other reactant needs to be? Okay, our products are carbon dioxide, but our other reactant has to be oxygen gas. So our products are carbon dioxide and what? H2O. So we need to balance this now. Okay, I think that's probably balanced. 2 carbons, 4 hydrogens, 6 oxygens, and 6 oxygens. Okay, and you'll notice in this problem it asks you how many grams of carbon dioxide can be formed. So what product do you need to go to? Yeah, I need to go to grams, but specifically do I need to go to carbon dioxide or water? Yeah, you could waste your time going to water to find your limiting reactant. Then you'd have to do another T-chart to find out how many grams of carbon dioxide could be formed. So you might as well just go to carbon dioxide the first time. Okay, why don't you go ahead and try this one on your own? I'll be around if you have questions. So limiting reactant should have been O2, and the maximum amount of carbon dioxide that could have been formed should have been about 2.9 grams of CO2. Right? So once you determine your limiting reactant, everything is based off of that. There'd be no reason to look at our other set of reactant because that's extra. It's excess. Okay, so once you determine your limiting reactant, any T-chart you do from there has to start with your limiting reactant. And that's what we're going to look at next. Okay? So now we're going to look at finding the limiting reactant, and then we're going to find out how much extra of our other reactant is left over. So excess reactant. Okay? We're going to find our limiting reactant and we're going to look at how much excess reactant is left over. There's lots of different things we can do once we find our limiting reactant, and this is just one of them. Okay, 45 grams of iron react with 87 grams of oxygen gas. What's my limiting reactant? What's the maximum amount of iron oxide that could be formed? And how much excess? So you're answering 3 different questions here. So this problem is going to take quite a bit of work. So if you want to, jump to a new page or whatever, you're going to have 3 T-charts here. Just telling you off the bat. Okay? First thing that we have to do is find our limiting reactant. So you know how to do that. Okay? We'd go 45 grams.
It's not balanced. Yeah.
It's not balanced yet? You're right. So we need a... that? Because we need an even amount of oxygens. So 4 irons, 6 oxygens on both? Okay, thank you. I had this is a 4, even though it's kind of hard to see. Okay. So 45 grams of iron, and I'm going to go, I only have one product, so I'm going to go to iron oxide. I'm going to go all the way to grams in this one, and I'll explain to you why I did that here in a little bit, okay? Technically, you could just still go to moles. Whatever you choose to do is fine for this part of it. So that means our limiting reactant is which compound? Good. Good. Limiting reactant equals iron. And what's the maximum amount that could be formed? 64.4 grams. Okay, so that answers 2 parts to our question. Are we good with that part so far? Okay, so now it wants to know how much excess is left over. So which of our reactants is our excess reactant? O2, right? So we're not going to use all 87 grams. But what we need to figure out is how much of our 87 grams is going to get used. And then we're going to subtract that from 87 and find out how much is left over. So the way we do that is we compare that, or we use our conversion, our T-chart conversions, to go from our limiting reactant. So we'd start with 45 grams of iron, and we would go to grams of oxygen. And we'd say, if we used up all 45 grams, how many grams of oxygen is used, right? That's what that T-chart is telling us. So we'd go from grams of iron to grams of O2. That's our goal here. Okay, so what this tells us, this does not tell us the amount left over. This tells us the amount of oxygen gas that is used. Okay, did we get it to come out at 19.4? Okay, this tells us how much has been used up. So if I use all 45 grams of iron, I'm only using 19.4 grams of oxygen. So to find my leftover amount, I take... This is grams, because the reason I went to grams is because my starting amount was in grams. It'll be grams. So I'm going to take my starting amount of oxygen, which was 87 grams, and I'm going to subtract out how much was used. And that would tell me how much I have left over. Sorry, that's kind of hard to read. 67.6. Okay, that's how much is left over. The reason I went to grams on this last T-chart is because my starting amount was in grams, and I knew I was going to have to subtract. The first two, these ones, you could have just gone to moles if you wanted to find your limiting reactant. Okay, it's not that big of a deal. You just have to be careful about what the question is asking for specifically. Okay.